Very happy to see you this morning. You know why. At least there's a few people who are serious about science. A few words for the Ukrainians who are still fighting for their freedom and for our freedom. Today, first, I want to talk about two things. First, what is declarative programming? I keep saying how wonderful it is and I show how to use it. What is it exactly? So I want to show that. And then the second thing is I want to show some very advanced techniques for building declarative algorithms using single assignment and lazy evaluation. You can make them very efficient. This is stuff that is difficult to find in books. In my view, there's only one book really that discusses the advanced techniques, which is this one, Purely Functional Data Structures by Chris Okazaki. So you can take a look. It's using OCaml, so it's not using Oz or Haskell. So, but it's a very, very interesting book. Okay, so let me talk about declarative programming first. What is it exactly? We have seen a number of paradigms. Okay, 5 paradigms. Sequential functional programming with single assignment, which allows to make tail recursive list functions. Deterministic data flow, so the concurrent stream programming, lazy evaluation, and the combination of laziness plus concurrency, which allows to do things like the bounded buffer. So I'm telling you they're all declarative. But what does really that mean exactly? In the previous course we talked about lambda calculus, but these things are far away from lambda calculus. Okay? So let me explain. That's the first thing I want to explain today. Okay, so it all starts at the lambda, from the lambda calculus. All functional programs can be encoded as lambda expressions. So I'm not going to redo all the lambda calculus, but I want to mention one very strong property, which is called the Church-Rosser theorem. I won't show the proof, but you can find it very easily on the internet. If I have an expression, EA, okay, on the top left, and I reduce it, so I'm executing the program, and I reduce it in choosing some reduction steps, and I go to EC. But I can also choose other reduction steps. Usually there's many possibilities. I can go from EA to EB. Now the Church-Rosser theorem says, if you do that, you can always find an ED such that both EC and EB will reduce to ED. They will always come back together, okay? So this property is also called confluence because it's flowing together, or the Church-Rosser property, okay? For programs that terminate, this ED is the final result. But this is true also for programs that don't terminate, okay? So this is the fundamental property that we're starting from. This is a very strong property, which is one of the reasons why the lambda calculus is the foundation of all programming languages. Okay, so sequential functional programming, which is the first paradigm, is clearly confluent. It's clearly functional because there's a fairly straightforward translation to lambda calculus, which we saw in the previous course. All the operations, you can encode them as lambda things, and it's just doing lambda reduction. But we actually went farther in our course in declarative programming. We add concurrency, threads, okay, and a scheduler, fairness. We add streams, which is programs that never terminate. Okay, the stream keeps growing and there's an output stream. We also add single assignment variables. Variable can be unbound, but you can bind it to one value. So what does it mean when for these things to be declarative? Okay, so I'm going to show you each of these 3 separately, and I'm going to show you in 3 parts. First of all, I won't spend so much time on concurrency because confluence handles that. Threads, all that does is it changes which reduction is done at every step. The scheduler chooses the reductions. But because of Church-Rosser, this is fine. Okay? So I won't talk about this one more, but I will talk about the other. Streams. So these are programs that never terminate. You keep feeding an input stream, an output stream keeps coming. What does it mean? So for that to be declarative. So I will talk about partial termination, where the program actually can kind of stop, rest for a while, and then continue. And finally, what does single assignment variables do to this? Well, single assignment variables is a very major, big change, because it leads to this fun paradigm being a kind of logic programming. So the stores, equivalent stores, so when you have stores with unbound variables in them, the bindings can be, the variables can be done in different orders, but somehow the stores are still the same. So the equivalence is kind of logic. So I will give you an introduction to first order logic to explain that. Okay? Okay, so let me go step by step. The first is partial termination. Okay? So here on the left we have a concurrent agent. The code is easy. I won't write the code. We have an input stream and an output stream. And it just multiplies each element by 2. So if the input stream is 1, and then unbound variable, the output will be 2. And if the input stream is extended, the output will extend it. So how is this functional? Because this program doesn't terminate. This input stream can always go farther. Also, the streams have unbound variables. Okay, what does that mean? Okay, so first I'll talk about termination. Well, we can actually define a kind of temporary termination. If S1 does not change, okay, so if you do S1 is 1 underscore, and then you just leave it like that, then the program will execute and it will at some point terminate. It will stop, it will finish, and the output will have a particular value. Okay? So if the input does not change, the output will eventually finish executing and get a value. So this is, I call this partial termination, because the program is not really completely stopped, because it can keep going again. But for now, it's temporarily stopped. And the point that it reaches is called a resting point. So it's like resting for a while. But then if you continue binding S1, like 1, 2, then the output will also be extended, but then you have a second resting point, or a third one. So as this stream, input stream, is extended, the program goes from one resting point to the other. And all of those are, in some sense, functional executions. So S2 is a function of S1, always. Okay? So that is how we can define functional execution for programs that don't terminate. Okay, so that's the first thing. But what about the unbound variables? So this is straightforward. Huh? The unbound variables. Okay. So here we have to talk about two stores with variables that are bound differently, but somehow they're still the same. Okay. So here, let me give you an example. So we have a functional program that uses single assignment variables, and I'm claiming it's still functional in some sense, which I will define. Well, here's a simple program with two variables, x and y, which are bound to records. X equals foo zw, y is foo zw, and the third thread just does x equal y. Now, the bindings in the store, it depends on the scheduler. Okay? If T1 and T2 execute first, then X will be bound to, so this is a store sigma, variable X will be bound to this record, and Y also to a record. And then, when I do this, T3 will basically do nothing because they're equal. But assume we have the scheduler makes a different choice. Let's say it chooses T1 and T3 first. Then T1 will bind X, And T3 will bind x and y. So y will be bound to x, but not to foo. But you can see this x here is actually equal to foo zw. So in some sense, these two are still the same. Okay? Even though the actual bindings are different because of the scheduler, in some sense, these tors are still the same. So how are they the same? Okay, how can we express that? Well, in order to do that, I have to give you a small introduction to first-order logic. So I will now give you an introduction to first-order logic. So this is an independent thing. So you have already seen some first-order logic, right, in the previous course. So this hopefully will be a refresher. But if you did not see it, then it's okay, because this is kind of self-contained. So this is a very, very brief introduction to first-order logic. Okay? So we introduce first-order logic. So I do it in a step-by-step. So I will basically define the concepts, so you will see precisely what is a formal logic. But we're not going to do too much theorizing on it. I just want to show you the concepts. So first of all, formal logic. So formal logic is a form of mathematics which mimics reasoning processes. But technically it's three things. Okay? It's a language, like a syntactically defined language, like it could be formulas in some kind of a form. And for each formula we want to know whether it's true or false. And then we have two other things. We have what's called a proof theory, so we can actually do deductions. Okay? So simple deductions, like if we have x equals 5 plus 6, we can make that x equal to 11. That's a form of deduction. Okay? So it's a set of rules to deduce whether a formula is true or false, given a set of primitive formulas. So we assume there's some formulas that are assumed primitive, we call them axioms, and we have a set of rules that allows combining them to make inferences. That's called the proof theory. Okay? So that's purely syntactic. But the third thing is kind of what really makes it grounded. This is called the model theory. Now, if a formula is true or false, it has to be true or false somewhere, in some world, okay? And that's called the model of the axioms, okay? And I will give you an example of that. So now this is true, what I showed here is any formal logic. So there are many different kinds of logic. There's propositional logic, first-order logic, second-order logic, which I will not talk about, modal logic, so all kinds of different forms of logic. But I will present only first-order logic. In some sense, first-order logic is a sweet spot. It's kind of the nicest one in some very strong ways. Most of mathematics can be formalized in first-order logic, and you can build efficient theorem provers in it. So this is a very nice logic. So what is it? So it's a formal logic, but you have variables, like x and y. You have quantifiers for all there exists. You have predicates, which is basically a relation with multiple arguments. And you have these connectors, which are, this one is and, conjunction, equivalence, and so on. You have other connectors that I won't talk about. With this, you can build expressions, okay? So here, for example, for all x, for all z, grandparent of xz, if and only if there exists a y such that parent xy and parent yz. So that's a syntactic formula. It may be, you might think it means something, but that's only an illusion. This doesn't mean anything, it's just symbols. Okay? This could be blue, blah, and blee, for example, and you don't know what's going on. It's just a connection between relations. But we can give it a meaning by adding a model. And the model for this one could be a set of human beings with the human parent relation, okay, in there. So you have parents, mother, father, children, so there's actually an actual parent relation between real human beings. And then you can kind of make a mapping of this syntactic thing to real human beings, and real human beings who are parents or children, okay, or grandparents. And then this axiom has a meaning. And maybe it's true or false. It turns out this one is true. You can say it's going to be true. It's actually defining grandparents in some sense, huh? So this axiom would be a true axiom in this particular model. Okay. So you can see how this axiom is just a bunch of syntax, and the model is an actual thing. It could be in the real world, or it could be a mathematical thing, structure, in which the axioms are true or false. Okay? So that is the two parts of any formal logic. Now, you can actually build programming languages based on this. Okay? The most famous one is called Prolog, which was created in 1972. So last year was the 50th anniversary symposium of Prolog, which is still used. You don't see it so much, but it's still widely used. There's many very good Prolog systems, and you can download them for free. Okay? And it's based on first-order logic. It's actually a theorem prover in first-order logic. There's also constraint programming. This is a descendant of Prolog. Prolog kind of created constraint programming. This is a very active research topic. It's a very powerful paradigm, okay? But it's doing first-order logic. And there's one that everybody knows, SQL, which is for doing database queries. Well, a database and the queries in a database, it's just doing logical inference, okay? So SQL is also based on first-order logic. So it's actually quite widely used, okay? So that gives you some idea. So this is refreshing your memory, right? So this is okay, huh? So I want to give you some examples because I want to connect it then to declarative programming. So here are some examples. On the left, I have some syntactic expressions. For all x, x is less than x plus 2. That's pure syntax. It doesn't mean anything. There exists an x such that x squared minus 3x plus 2 equals 0, and so on. And I can have models. So there's a first model which is called z, which is the integers. Or I could have a model which is the real numbers. So I give some approximate definition, okay? So you could say the real numbers are all the numbers with an infinite decimal expansion. That's kind of an informal way of defining them. But all the formulas on the left are true in both of these models. If we assume that these symbols are given the right meaning. So this is subtraction, addition, and so on. Square operation. That's an example. Okay. Now I want to introduce some notation now because we're going to go back to declarative programming, and we need to have some precise notation. Okay, so we have some formulas, which I showed you examples, and F is the set of formulas, and alpha and beta are just some random formulas, like the ones we saw in the previous slide. Now, we can actually do some kind of logical notation on these formulas. And I said there was proof theory and model theory. So there's two ways you can connect the formulas. You can say, for example, A can prove B, or B can be proved or deduced using the rules of deduction given A as an axiom. And this is denoted with this turnstile operation. This is a proof. With A, I can prove, with alpha, I can prove beta. Okay? So, given this, if this one is alpha, it exists in x such that x squared equals 1, then I can prove that x equal 1 or x equal minus 1. Okay? So, this is pure syntax. It's proof. So, a running program could actually do this, and that would be called the theorem prover. Okay? But that's not the only connection. The other connection is in terms of models. So a model is like a real-world structure in which the formulas can be true or false. So here I have beta is true in all models in which alpha is true. Okay? So if I have any model, and in that model alpha is true, then this is stating that beta will also be true in that model. Okay? So here's an example. If this formula is true in the real numbers, then this formula will also be true in the real numbers. But I can replace R by any model in which that is true. Okay? The real numbers is just one particular model. There can be many, many, many models for a particular axiom. Okay? So these two notations are very different. So the first one is basically syntax. You can make a proof, okay, sequence of deductions. And the second one is what we call the semantics. It's talking about truth in the real world or in some mathematical structure, okay? Wherever alpha is true, beta will be there, which would be true there as well, okay? So these are the two kind of connections we can make. So is this familiar to you? Have you seen this before?
Oh, yes.
Yes? The difference between proof and model?
Yes.
You've seen that? Everyone has seen that? Great. Okay, so I'm happy. That means that's good. So it's important to have some basic understanding of this. Now I want to go back to our declarative program. We have the storage sigma. Okay? We want to define a model of the store. So the store sigma is just variable bindings, okay? So the model, actually we can build a model, but usually it's done in two steps. We first make what's called an interpretation of the store. An interpretation is all the symbols, we assign things to them. So if we have this binding in the store, x equal f x1 to xn, then the f, this is just syntax. We will make it correspond to a function. A function with input variables, input values, and output values on some domain. So this is part of the model theory, okay? Okay, now if the store has this binding in it, then this is going to be true if the value returned by this function is equal to the value of x. So all the variables, we will also make values assuming to them. So for example, the variables could be real numbers, and f would be some function on real numbers, okay? So if we have a store sigma, it's a bunch of these bindings, okay? It's a conjunction. So x is bound to something, etc., z is bound to something. So if all these bindings are actually true in the real object, the mathematical object, then the store is true. So an interpretation is kind of precursor to a model because formulas might be true and they might be false, okay? But the model is the interpretation where all the sigmas are true, okay? And the model is actually respecting all of the bindings in the store, okay? Okay, so that's an introduction to first order logic. So there, now you know first order logic, right? Okay? So now we go back to our program here. We have run this program, 3 threads. We have sigma and sigma prime. And they're different. I mean, the bindings are different. But in some way, in some sense, they are the same. How are they the same? Okay. So assume we have sigma and sigma prime. The result of 2 executions of a declarative program. So they look different, but they're actually the same in some sense. Okay. The bindings are different, but the possible values of x and y are actually the same. Okay? So each store is like a relationship. So sigma says that x is a record with labeled foo and arguments. Y is a record with labeled foo and arguments. So that we can define a function that actually builds a record structure in memory. Okay? And there's actually 4 variables in those stores, x, y, z, and w. And we can take any values. We can assign values to these variables. And there's 2 possibilities. Either they are true in sigma, or they're not true in sigma. If we bind x to a number, then clearly it's not true because the x's should be a record. Okay? So the store sigma is actually a logical formula, which could be true or false in the particular interpretation. So we can write it as a logical formula. So let me write it as a logical formula. Okay? So the store there with variable bindings, which is a set of variable bindings, we can actually consider it to be a logical formula. Okay? Now we can say when the stores are equivalent. Okay? So intuitively, first intuitively, and then I will make a more formal definition. So each store represents a logical formula which can be true or false depending on the values of the unbound variables. And 2 stores are equivalent when no matter how we assign values, they're either both going to be true or both false. We cannot make one of them true and the other one false. Okay? So they're basically saying the same thing in a sense. The set of values for which they are true is exactly the same. Now we can write that using logic notation. Remember this notation. So all the models of alpha are also models of beta. Beta is true in all models of alpha. Now alpha and beta are actually logical formulas like sigma. So 2 stores are logically equivalent if I have a model that makes sigma true, sigma prime will be true, and inversely. Sigma prime is true in all models of sigma. Sigma is true in all models of sigma prime. Basically what that means is that they're saying exactly the same thing. If I have a model of them, of the formula, so a set of values that makes them true, that sigma and sigma prime, it's expressing the same set. So you can also write it this way, the same. So here I have another logical formula, sigma, if and only if sigma prime. And this notation, when I don't put an alpha, it means it's true in all models. So this one is a tautology. That means in any model we look at, any one at all, this will always be equivalent to that. Okay? So the stores are saying the same thing. You see? They're basically expressing the same set of values. Okay? So that's all I want to say about logic. Okay? And now we can actually define declarative programming. Finally, we get to definition, which is actually, after all of this, it's actually very simple. Okay? What is declarative programming? So I have a program, and I run it. And the program is declarative if for all possible inputs, all executions, so no matter how the scheduler chooses it, either they all do not terminate, so they're all infinite loops, or they all reach partial termination and they give logically equivalent stores. So they basically end up in the same place. Okay? So either they don't, they both go infinite loop, but it's never the case that one of them is infinite loop and the other one is stopping. Do they always all go into an infinite loop, because you can have programs that are infinite looping, or they all will reach some partial termination, and once they do that, the stores are logically equivalent. Okay? So this is for concurrent programs, all possible choices of the scheduler. So one way of expressing this, which I said always before, the program has no observable non-determinism. Which means that even though the scheduler is free to choose non-deterministically, so it can choose independent of the programmer, you can't see that because the stores will be logically equivalent. I mean, the actual bindings might be different, but they are logically equivalent. So all the 5 paradigms we saw are declarative in this sense. So they're always giving logically equivalent scopes. Okay. Okay, so that's declarative programming. Okay. So this is an observational kind of a property. It depends on the programmer's behavior. So these are not necessarily implemented using lambda calculus. I mean, lambda calculus will give this, but this is a little bit more general than that. Okay? Okay, so I want to talk a little bit more about that. Something which I call failure confinement. So declarativeness is very powerful, and we have seen some of the good properties. A program that is correct will always be correct. There's no race conditions, so all the concurrent programs are simple and so on. And so one of the themes of the course is that all programs should be declarative, except where they can't be. And we will see later that's where they interact with the real world. So there's some limitation. But we want to keep them as declarative as possible. But what if the application becomes non-declarative? Okay, so there's several ways. An application that interacts with the real world can be non-declarative, because the real world can introduce observable non-determinism that you cannot get rid of. So their stores will no longer be logically equivalent. Okay, but you can also have a bug that makes program non-declarative, or some weird behavior, but that you can hide. You can mask it off. You can, if there's, I mean, bugs are unavoidable, okay? So you can say it is a truth universally acknowledged that a program of a certain size must have bugs. So if you have read Jane Austen, you know where that phrase comes from. No? Pride and Prejudice. So here's a simple program. X equal 1, y equal 2, x equal y. This one will always raise an exception. Okay? Depending on the scheduler choices, we have 3 possible stores. X equal 1, y equal 2, x equal 1, y 1, and x equal 2, y equal 2. These are not equivalent. Okay? This is an observable non-determinism. And this can happen for many reasons. Maybe failures, or maybe there's something where things are happening in different orders. Okay? So we may want to keep going and still have a declarative program. So we can hide this and make the program declarative again. So we can kind of encapsulate the non-determinism, non-declarative. And this is called failure confinement. Okay, so here's one way to do it. So we are now I'm showing some non-declarative programming here. The way to manage the declarativeness, to increase the declarativeness. So assume we have our program, okay, which is x1 equals 1, y equals 2, x equals y. When we write it in a different way, and if there is an error, then we have an exception. So I'm not going to explain it now. I just want to show you. If an error has happened, then one of these 2 variables will be bound to error. And then I say the result is always x equals 1, y equals 1. And when there's no error, I just pass the result of the program. So I'm basically masking the error. Okay? So that's something you can do. Okay. Okay, so now let me kind of summarize. There's lots of declarative paradigms. So this figure comes from the book, the thick book, Concepts, Techniques and Models of Computer Programming. And we saw all these, but you can actually technically do a little bit more. So you have eager and lazy in the horizontal, in this direction. Then you have values and data flow variables, so single assignment and concurrency. So we have seen different kinds of functional programming. Strict, lazy, so the language Haskell does laziness but does not have unbound variables. Then we have other languages that do strict functional programming, Scheme and ML. We have languages that are eager, that are not lazy, but use unbound variables. So Prolog does that, but Prolog does more than that. But Prolog logic programming does that. And then we have the concurrent logic programs, So there's no really named languages here. This is funny, huh? But this model does exist and it's used a lot. Okay. So these are typically used in cloud analytics tools when you have stream processing. Okay. Okay. Okay, so let me summarize then the part of the course on laziness and declarative programming. So we saw laziness, okay, and it's semantically very simple. We have data flow with wait and bind, and we just add one operation when needed. And programs are much more general. We can use infinite lists, and we can combine with concurrency. So this is very powerful. And then we've defined declarative programming. We define what it is in terms of confluence, partial termination, modular of equivalence, and it's observational. That means it's something we see, the behavior. A whole program can behave declaratively even if it's written in a non-declarative paradigm. So it doesn't have to be written in lambda calculus. But even though lambda calculus is declarative, you can be more general than that. You can have programs that are written in a non-declarative paradigm but still behave declaratively. Okay? Okay, so now we will go to the second part of the course, bigger part. This is the final lecture on declarative programming, the most subtle one. It's about designing algorithms. So I'm going to show you how to design algorithms that are declarative and efficient. Okay? So the motivation is writing efficient algorithms in declarative paradigms. People will tell you that declarative languages are not efficient. That's not true, actually. Okay? And I will show you some techniques I will show for writing efficient algorithms using single assignment and lazy evaluation. So we will make different kinds of algorithms, amortized and worst case, but also ephemeral and persistent. So we'll see algorithms maybe that you have not seen in an algorithms course. We'll be a little bit more general. Okay? And I'm going to give a certain number of techniques. First, what's called a difference list. So a list with efficient operations, like append. These are ephemeral, which we will see what that means. So it's basically very efficient lists. And then I will show you different ways of doing very efficient algorithms. And we can see them here. So I'll have one example which is kind of the standard one, and I'll write it in different ways. A queue algorithm. And I will make different versions. So constant time queue, worst case constant time, then what's called a persistent queue, and worst case persistent. And we'll see what that means. Okay? Okay, so the motivation is, and this is a kind of theme for this course, as much as possible of your program should be written declaratively. And that has many, many advantages. So the algorithms too. Okay? Can you make efficient algorithms in declarative paradigms? Do you really need assignment, mutable state? Well, not really. Okay? You can make declarative algorithms, you can always make them efficient. And I'll show you how that works. So some of the examples are coming from this book, Purely Functional Data Structures by Curtis Okasaki. So this is a very interesting book on how to use lazy evaluation to make efficient algorithms. Okay? And it uses a functional language called standard ML, extended with an explicit laziness operation. Okay, so now let's go into the course for algorithms. First, what concepts? So we're going to look at different kinds of algorithms, okay? And let me define them. So this is actually going farther than what you'll see in normal algorithms courses, huh? So we'll have language concepts, complexity concepts, so this is the time complexity, but also different kinds of algorithms. So I'll talk about ephemeral and persistent algorithms. And this is a very interesting distinction, very important, okay? So the language concepts, we saw them before. It's basically two, single assignment variables and lazy evaluation. Those are the two declarative concepts we're going to use, okay? Complexity concepts, we're going to look at time complexity, which you have seen, right? In an algorithm course. Have you seen both amortized and worst case?
Yes.
Okay, very good. So this will be a refresher. So we're going to define amortized algorithms and worst case algorithms. And finally, we're going to look at two different kinds of algorithms, which are called ephemeral and persistent algorithms. You may not have seen persistent algorithms. Most of the algorithms you see in algorithm courses are ephemeral. So we'll see what that means, okay? But persistent is very important. Okay. First, I want to introduce a refresher memory on complexity, on two kinds of complexity we're going to talk about. So this is time complexity. So it's basically an upper bound on the execution time, modulo a constant factor. And we're going to talk about amortized and worst case. Okay, so worst case, I'm not going to define. It's the big O notation, which you have seen, right? Which basically gives you an upper bound within a constant multiplicative factor, okay? So it's like a ceiling. And so the execution is below some value given big enough inputs. So that's the worst case complexity. But a very important concept also is amortized complexity. If you have n operations, and if you combine them all together, the complexity is O f of n, then you say each of those operations has an amortized complexity of O f of n divided by n. So it's like you're spreading the f of n over all of the individual operations. So this is important, because sometimes you have n operations, and one of them is very expensive, but all the other ones are very cheap. So it's kind of very cheap on the average, but occasionally there's a very expensive operation, okay? And that happens a lot in algorithms that do things. For example, tree algorithms are usually very cheap, but sometimes they have to reorganize the tree, which is expensive. So that means sometimes I do an operation which has O(n) complexity, but most of the time it's O(1). So amortized is a way of formalizing that, okay? So if I have a queue, the individual operations might have complexity O(n), but if I do n operations, these expensive ones are very rare, so that the overall complexity can still be O of 1. So on the average, it's constant time, even though once in a while there's an expensive operation in there, okay? So this is very, very common for algorithms. It's actually very hard to make them always cheap. Sometimes you can do that by making everything very incremental, but very often it's cheap on the average, okay? So amortized will formalize that. So this is what we're going to look at, these two kinds of complexity. So this you have seen, huh? So you know this stuff, huh? But now I want to introduce something new, which is two kinds of algorithms, ephemeral and persistent. This depends on how many versions of the data structure. So this is very interesting. So let's say I have a queue, Q1, and I do Q2 is equal insert Q1, I put A in the queue. In an ephemeral algorithm, if I do that, then Q1, I can't use it anymore. So basically, I've created a new version, Q2, but the old version, I can't use it. It's gone. So if I write algorithms in Java, it's almost always like that. If I have a queue data structure in an object, and I do kind of mutable updates, well, the old version is gone, okay, because I've updated it. So almost all stateful algorithms are almost always ephemeral. That means you can only have one version at a time. When you create a new version, the old version is no longer available, okay? So that's the normal way. So almost all algorithms you see in a stateful language like Java will be ephemeral, okay? But sometimes that's not good enough. Sometimes you need the algorithm to be stronger than that. And that's what's called a persistent algorithm, or persistent data structure. You can have many versions. So let's say I have a Q1, and I do Q2 is equal insert Q1A. So this creates a new Q2, but Q1 is still available. So if later on I can still use Q1. So when I create Q2, it doesn't destroy Q1. So that's actually interesting, huh? All versions are still usable. So you might say, what is that good for? Why do you want to do that? Because usually you only want the most recent version, right? Actually, no. Very often you want multiple versions, okay? Now, I introduce it because with laziness, we can actually very easily write persistent algorithms, which are very hard to write in stateful language. So this is a case where laziness is actually giving you a lot of power, okay? So why do you need persistent algorithms? Well, it's used a lot. You have already used it already. For example, people are editing the same text, and they create their own versions, okay? Or you have software repositories. So you've probably all used GitHub. GitHub supports multiple versions, and you can branch out. You can also merge them together, the versions, but you don't have to. You can have multiple versions. So if I create one version, the original version doesn't disappear, okay? Also, there's a number of databases, commercial databases, that also support multiple versions, which can be very important when you want to do things like a rollback, for example. You want the old version to still be existing in some sense, okay? So that's actually very useful. But usually you have to program it explicitly if you do it in a stateful language. You can do explicit copy operations. So in GitHub, you have to explicitly create a copy or version, okay, or branch. So that's kind of clumsy. You have to do it all by hand, okay? But in the code I will show you today, it's all automatic. You don't have to worry about it. And then there's one extra operation sometimes you have that you add in persistent algorithms. This is called merge. So if I have a queue and I'm making I have two versions, for example, sometimes I want to combine them again. Combine versions to create one version. So that's something that doesn't even exist in an ephemeral algorithm, because you only have one version. But here you can have many versions. Maybe you want to combine them. Like two people are working on a text, and you merge them. And this is often done kind of automatically. So the merge operation usually is a little bit smart. It's taking care of conflicts. So if I merge two texts, if there's two people have edited the same line, it will somehow decide how to do that, okay? So persistence is a very useful thing, okay? See ya. Okay, so what am I going to show you today? I'm going to show you the same algorithm, the same data structure, Q, but with different algorithm, different code, okay? Different implementations. I'm going to show you 5 ways to implement the same Q. So it's exactly the same Q with exactly the same interface. So I can use it, and I don't know which one I'm using, but it can be any of these 5. Okay, so I'm going to give first a naive Q written in sequential functional programming. The naive one, the insert is constant time, and the delete is not constant. It's O(n), where n is the size of the Q. Okay, so that's kind of naive algorithm. And you see the delete is not very nice here. Huh? It's O(n). So I'm going to show you better ones. I'm going to show you that in amortized ephemeral Q, where both insert and delete are constant time. That's nice, huh? That's like how you would do it in Java, except it's declarative here. Huh? Both of them are constant time. Okay? But it's amortized. Because sometimes they're expensive. Well, that's not so nice. I can actually make it better than that. I can make it worst case constant time. That means all of the operations are always constant time. Okay? If you add single assignment, you can do that. So the single assignment lets you make very efficient ephemeral algorithms. Okay? Okay? And we can go even farther. If we use lazy valuation, we can actually make very efficient persistent algorithms. So if you want to make a persistent algorithm, laziness is kind of the best way of doing that, okay? Because it's all done automatically as part of the lazy valuation. You don't have to do any really explicit management of the versions. Okay? It's all kind of automatic. And I'll show you an amortized persistent queue where all the operations are constant, but these constants amortize. So sometimes it's expensive. And then I'll show you a worst case persistent using laziness. This is a very subtle piece of code. This is maybe the most subtle code we're going to see in the whole course. It's even more subtle than the bounded buffer, okay? So it's very interesting to think about it and how laziness lets you make efficient algorithms, okay? So I make a kind of tree to summarize what we're going to see. So we're going to look at a queue, and we're going to look at ephemeral queues and persistent queues. In the ephemeral queues, I'm going to show you an amortized constant time one. This is written in sequential functional programming. And then a worst case constant time. This is when we add single assignment. So single assignment lets you do worst case constant time. So always constant. Okay? And then persistence. Persistence is what laziness gives you. With laziness we can make both the amortized and the worst case. I make them separate because this worst case one requires some subtle technique, some more subtle thinking of how the thing is running, okay? So it's interesting to split them. The simplest one is just amortized, constant time, but it's persistent. That means you can have many versions as you want, and it's still going to be constant time. That's pretty amazing, okay? It's very hard to program that if you want to do it in a non-declarative way. So that's what we're going to see, but let me make a break now, and we'll see the code after. Queues using single assignment and lazy valuation, and used in a kind of very clever way to make efficient algorithms, okay? But single assignment is so interesting that I have to show you another data structure first, which is a general one, very, very useful in all declarative programs, which is called the difference list. So a difference list is basically a list with very efficient operations. Okay? So a difference list is just a representation of a list. A list, 1, 2, 3. But I represent the list as a pair of two lists. And E is a suffix of S. It means it starts, and then at some point it goes on E. So the difference list SE represents the list S minus E. And I'll show you examples in the code. But let me first show you some examples on the slide. So if I have a list 1, 2, 3, nil, I can represent this as a difference list. So the difference list is two variables that represent one list. So there's many ways. So I can represent it as the pair 1, 2, 3, X followed by X. And X, it doesn't even have to be bound. X is an unknown variable, which could be bound to any list. Don't care. So this structure represents the list 1, 2, 3. X, but minus X, so the X disappears. So it's only 1, 2, 3. Or I can even go farther. 1, 2, 3, 4, Y. And the second element is 4Y. So that means this 4Y minus this 4Y, it's still the list 1, 2, 3. Or I can have them with no unbound variables. 1, 2, 3, 4, 5, nil, and then 4, 5, nil. So the 4, 5, nil disappears, and I still have 1, 2, 3. So there's an infinite number of ways of representing a list as a difference list. So why do we want to do this? Why do we want to represent the list 1, 2, 3 nil as two variables? Because it's very efficient. Okay. All the operations on lists become very efficient. Okay. So I have to show you some code, some running code on this. And then we'll go back to the slide. So a difference list. Okay, so let's say I have a list. And L is the list 1, 2. Fine. Fine, 1, 2. But I can represent this list as a difference list also. And I can say, for example, that S is equal to 1 part 2 E. Okay. So, okay, fine. If I do browse S, I get 1, 2, but unknown variable. But S is not the list. The list is S minus E. Okay. Now let's say I take another list. Difference list. S2, E2. S2 is equal to 3, 4, E2. So this is another difference list, okay? So it's not easy to display, of course, because it's the two variables. So it's S2 minus E2. So I have two lists here, okay? Represented as difference lists. I have the list 1, 2, nil. And here I have the list 3, 4, nil. But now I can do very efficient operations. If I want to append them, of these two, I can append the two lists. And how do I do that? Well, let me show. So I have 1, 2, E. So this represents the list 1, 2, nil. Okay? So this variable is S. Now I have the other list, which is 3, 4, E2, E2. So this is basically S2. This represents the list 3, 4, nil. I can append them in one binding. Let's say I want to append these two lists. What do? I want to create a new difference list. What do? Well, here I have 1, 2, E minus E. Well, if I bind E to S2, and then I take S and E2. So I bind E to S2. So basically, I'm kind of short-circuiting. The E will be bound to S2. So the S will be 1, 2, 3, 4, E2. And the resulting difference list is S, E2. So basically I have SE and S2, E2. And I short circuit the middle and I take S and E2, and this gives me a new difference list. So the difference list is S, E2. This is exactly the append of the two lists here. But this binding is constant time. But if I would run append as a function, it would take time proportional to the length of the list. But here I have appended the two lists in constant time using the difference list representation. Okay. So here is the explanation on the slide. So if I have two difference lists, S1E1 and S2E2, okay, I can append them all I have to do is bind E1 to S2, and the result is given by the list S1, E2. So S1, which is from the first, and E2, which is the end from the second, and I basically bind E1 to S2, so I'm kind of short-circuiting the middle. So if I have ABXX and 1, 2, Y, Y, if I bind X to 1, 2, Y, and I take the first element of the first difference list and the second element of the second one, I get A, B, 1, 2, Y, Y. This is exactly the append. You see, this lets me do append in constant time. This is the main advantage of difference lists. I can take two lists, declarative, and I can append them in a single binding. See, this is nice, eh? Of course, you can only do it once. Once the X is bound, it's over. You can only bind X once. The single assignment is only bound to one value, which means that it's ephemeral in our terminology, yeah? You can only do it once. But that's usually okay. When I have a program that's building a big list by connecting smaller lists together, well, I usually only have to connect them once. So this is fine. The fact that it's ephemeral is usually not a problem. So you see, the difference list has a major advantage over the regular list. Huh? You see that? And it's based on single assignment. It lets you do append in constant time. So it's much, much more efficient than a regular append. Okay? Okay, here's another use of a difference list, which is a little bit variation. If I have a difference list, I can add an element to the front in constant time. But that's something you can do with regular lists too. If I have the list 1, 2, 0, L equal 1, 2, 0, I can do 0 bar L, and the 0 is in front. Fine. But with the difference list, I can also add the element at the end in constant time. Okay? So if I have the difference list SE, where E is an unbound variable, if I want to add an element X to the beginning, all I have to do is S1 equal X bar S, and the result is S1E. But if I want to add X to the end, I essentially extend the E. I do E equal X bar E1, and the result is SE1. So adding X to the beginning and to the end is both constant time. Okay? So if I have the difference list 1, 2, 3, X, X, so this represents the list 1, 2, 3, yeah? If I want to add 4 to the beginning, I get this difference list. 4, 1, 2, 3, X, X. But I can also add X to the end by binding X. I bind X to 4 bar Y. This gives me 1, 2, 3, 4 Y, and it ends now with Y instead of X. Okay? So I bind X to 4 bar Y, and I take the first element of the original together with Y, and this gives me the element added at the end. So the E, or the X here, it essentially is like a pointer to the end, if you want. Huh? It lets me add something at the end. For a standard list with no unbound variables, 1, 2, 3, 0, it's not possible to add an element at the end in constant time. The only way is to traverse the whole list and create a new list, 1, 2, 3, 4, 0. Okay? So using difference list representation, I can add elements to the front and the back in constant time. And I can do append in constant time. Okay? This is very, very useful in programs. And I'll show you one example, which is flatten. Okay? So the flatten function takes an argument, which is a list of lists. So they can be nested lists as deep as you want, and it brings it all to the top. So here, this argument will give 1, 2, 3, 4, 5. 1, 2 is a sublist, 3, 4 is a sublist. But flatten will turn it into one list where all the elements are at the top, okay? So this is the naive flatten using append, the usual way. So here's append, I just show it for you. You see the append of L1, L2. It actually has to do recursion on L1. And so the time of this is proportional to the length of L1, the cardinality of L1. So if L1 is big, well, I have to go all the way down. But even though it's tail recursive, of course, so this one is already doing single assignment internally, it's tail recursive, but still it's time proportional to the size of L1. So here is the flatten written using append, okay? So XS is the input here. If XS is nil, then nil. Otherwise, there's different possibilities. So if XS is X bar XR, and there's a built-in function, and X is a list, okay? And X is a list, then I have to call flatten recursively on X, okay? Here, for example, 1, 2 is a list, so I have to call it recursively, and that returns, so flatten X returns a list, flatten XR returns a list, and I have to append them together. So I have to call append here. But that's not efficient, okay? Because the flatten X, this might be a long list, flatten X, and I have to traverse all the way down. Okay? The final case is when X is not a list, and then I just can add it. Then it's efficient. So, but here in the middle I have this call to append, which is not efficient. But I can get rid of this call to append if I use difference lists. So here's the difference list. So look at this code here. It's flattened, it has a single argument XS, and it returns the flattened. Okay? Now we replace the result by a difference list. But a difference list is 2 arguments, S and E. So I'm going to show it to you as a procedure, not a function. Okay? So I call it D flattened, D for difference list. So XS is the input, and SE is the output. SE is a difference list, which is the flattened output. So how does it work? Well, if XS is nil, then it's empty. Well, what's an empty difference list? Well, S is equal to E. That's an empty difference list. What if X is not a list? So I look at the third case. Then S is X bar M, and the difference list continues, ME. Okay? But this middle case is interesting. So here X is a list. So when I call deflatten on X, it returns a difference list, SM. And when I call deflatten on XR, it also returns a difference list. These 2 difference lists, I have to append them. But that's very easy. I just have to make sure that the second argument here is the same as the first argument here. SM and ME. And the result is SE. Okay, SE is the append of SM and ME. And because these are the same variable, the append is automatic. Okay? So this version of flatten does not need append at all. So it doesn't create any garbage. Whereas the first version will create a lot of garbage. It will make the garbage collector work plus do extra work. So the first version here, flatten X creates a list which I have to append. But the list created by flatten X is not needed anymore after that. So even though the append has to do extra work, but I'm also creating extra garbage here, the result of flatten X is basically garbage that the garbage collector has to collect. So it's not just running running append extra, it's also creating extra garbage. Whereas the difference list version creates no extra garbage. It's completely efficient. Okay? It's absolutely efficient. There's no append, everything's constant time, there's no garbage. So this is an extremely efficient way of doing flatten, But I can
let me run it. It's always good to run code. All right, you agree, yeah? Let me make sure I use the same notation. Okay, so let me declare the difference list version. It's a procedure because the difference list output is 2 arguments. I mean, I could return it as a pair, but the pair is also a data structure, so that wouldn't be so efficient. So for difference lists, it's common to make it, the output be a procedure. So if XS is nil, then I need the empty difference list. But an empty difference list is just where S is equal to E, okay? And otherwise I have X bar XR, and now I'm using a built-in function which checks whether X is a list. Okay. I do a deflatten X S M. This could be any variable, but I just choose M because I want to append them. XR M E. That's it. I have to declare M, of course. Huh? And the final one is X is equal to X bar M. So I'm basically appending X in the beginning, and then the recursive call is continuing with ME. Okay, so this is the deflatten, if I don't make a mistake. Okay, I can run it now. Okay. Let me do like this. It's a procedure, so let me run it with the argument that I give here. S is the result, and the final result is the difference list SE. But I don't care. I can turn it into a regular list by binding E to nil. So I give it as argument S nil, and S will then be a regular list. Okay, it won't be difference list. So I run this. And this returns 1, 2, 3, 4, 5. So this is the most efficient version. This is extremely efficient. Huh? It's hard to write even in any language. This would be the most efficient because it's basically implemented with pointers if you want. Huh? A variable bound to a value is just a pointer. So this is a very efficient implementation, which both in time and in amount of garbage. You see that? So in the previous lecture, we had a lazy quicksort, which used append. Actually, that's not the best way to do quicksort, because you can rewrite that quicksort to use difference list, which would be even better. So you don't actually need the lazy append, okay, if you use difference lists. So if you want to do an exercise, you can rewrite the lazy quicksort to use difference lists and not append. So usually, anytime you have a function which is returning a list and which is using append in there, alarm bells should ring, and you should say, that append is useless. You can always rewrite it using difference lists. So in the book, there's another example of a merge sort. Merge sort is an efficient sorting algorithm too, using difference lists, okay? So all algorithms that build lists out of smaller lists, you can implement them using difference lists, okay? And they're very efficient. Okay, I want to make a small comparison now. Difference lists between linked lists in Java or in C, C++, which are stateful. So a linked list is basically pointers, and you have an element, and there's a pointer to the next one, and so on, and it goes like that. And you can combine them by traversing the pointers, okay? And you can also have a pointer to the end. So it kind of looks like a difference list, in some sense. But it's not functional, okay? That's the problem. So what's the difference then? So both the difference list and the linked list allow efficiently building lists or chains of elements. But a difference list is qualitatively better because it's declarative. It has functional semantics. That means once you build it, you cannot change it anymore. It's cannot break it. As any functional program, it's a value. It's a constant. But a linked list in Java, you can always have a program that kind of messes it up. You can always modify it. So it's much more fragile, okay? The linked list, the difference list is a much more robust implementation, in fact, because of functional semantics. Okay, so that's interesting. That's for any program doing lists. Now let's get back to our queues, okay? Because we want to show you lots of things with queues. Let me first explain what is the queue, okay? The queue abstraction. So queue is a very simple kind of thing. It's a sequence, and it has two operations, insert and delete, okay? And the insert happens on one side, and the delete on the other one. So you can also say it's first in, first out. It's FIFO. So it's kind of the opposite to a stack. Stack, which is last in, first out. LIFO, a stack. I put an element, and if I want to take an element, it's the last one I get. Whereas in the delete, I insert 1, 2, 3, 4, 5, 6, 7, 8. And if I do delete, I delete 1. So I delete the first one that was put in. Okay? So this is a queue. Okay? So this is a standard data structure. I pick it because it's kind of non-trivial. And the code is not too complicated. So I can show you all of our algorithms would be implementing this. Okay? This thing. So I'll start with the naive one. So a naive one. Okay? So a simple queue abstraction. It's actually technically not a true abstraction because the inside is not protected. But that would add extra code. So I'm not going to show you that. But you can assume that the inside is protected here. So here's the implementation. It's very simple. New queue is just nil. So the queue is just a list. Okay? Insert will add in the front. And delete will remove the last element of the list. Okay? So insert will add in the front. So qx will become x bar q. And delete removes from the end. So we need a function that removes the last element. So here's a function called butlast, which takes a list and returns a new list, which is everything but the last element. And the last element is going to be returned here as an argument. Okay? So if the list has only one element, then it returns nil. And x is equal to y. Otherwise, it basically builds recursively. Okay? So this is our queue abstraction naively. So this is naive functional programming. Okay? There's no single assignment or anything. Okay? So I can actually, let me implement that. So the butlast function takes a list and returns a new list of everything but the last element. So if it's a list of one element, there has to be at least one element here. X will be equal to y and it returns nil. Otherwise, let me do it in the same way. Then I return butlast. L1 x. Okay? So this is our helper function. Butlast of 1, 2, 3, 4. Like this. Let me declare x here. So if I run this, it will basically return the list 1, 2, 3, and X will be the last element. Huh? 4. Okay? And now we can define our Q from this. Okay, so I have new Q. So the interface will be the same for all our examples. So an empty Q is just nil. Insert QX. We'll insert X to a Q and return the new Q. And delete. QX. We'll basically remove X and return the new Q. So it's basically but last QX. Okay, like that. Huh? And now we can run it, for example. So it's insert, new Q, A, B. Okay, so here I've just inserted 2 elements, huh? So it's B, A, okay? So the first element inserted is A, and the second element is B, and now I can do things like delete and so on. Okay, so that's a naive one. So what's the efficiency of this thing? The complexity? Well, insert is constant time, but delete has a time proportional to the number of elements in the queue, because it has to traverse everything. So that's not nice, huh? So this guy is, delete is always O(n), where n is the number of operations before. Okay, good. Let's make better. Let's do better now. We can at least make it amortized constant time in functional programming. So the previous naive one was actually way too naive. We can be a little bit smarter, even in the regular functional programming with values. Okay? This one will be amortized constant time ephemeral Q, which means that on average it's constant time, but sometimes there's an expensive operation. And how do we do it? Well, we represent now the Q as a tuple, Q of FR, where the F is elements in the front of the Q, and R is elements in the back, the reverse of the Q. So we can do an insert by updating R. If you look at the insert here, it's basically taking R and making X bar R. And we can do a delete by removing an element from F. F is equal to X F1. So the insert puts elements in R, and the delete takes elements out of F, and both insert and delete are constant time. Okay, now that's not good enough because the R and the F are not connected. We have to connect them somehow. So the way we connect it is that every once in a while, we'll basically take all the elements of R and put them in F. Like that. So if the F is empty, okay, we will put all the elements of R into F, but we have to do reverse R because the insert basically inserts them in the opposite order that they're taken out. So we take reverse R and move it to F. And that's done by a helper function called check up there. So you see how it works. The insert and the delete are constant time. Here, constant time on average. But they all will run check. So the check will make sure that if the F is nil, here we have nil R, it basically moves all the R's into F. So it returns Q of reverse R nil. So you see how it works? But if it's not nil, it does nothing. So we have to do the check all the time, because we never know when the the f might be nil. Each time we do a delete, it might be nil, okay? We also do it in the insert to make sure that if the f before was nil, that it's not going to be nil afterwards, because we might be doing a delete after, okay? So we have to do the check also here. But if we do multiple inserts, it will only do one reverse, of course. Now once all the elements, once the f is not nil, it's happy, okay? But when we do a delete, if the f becomes nil, then it has to do again a move from R to F, okay? See how it's working? Why it's amortized, okay? So let me show you a kind of picture of how it runs. So on the top, we have the naive queue. And on the bottom, we have the smart one, the amortized constant time ephemeral queue with the F and R lists. Okay? So the naive one, how does it work? Well, the insert is constant time. So each little arrow is an operation. Ins means it's an insert, and the 1 is giving me the time. Okay, 1, 1, 1, 1. All the inserts are constant time. So assume I'm doing n inserts. And now I do a delete in the naive version. Well, I have to do but last, and there's n elements. So it's order n. And then I do another delete. Well, again, it's n, order n. It's n minus 1, n minus 2, and I can delete all the n elements. So here I have n minus 1, n minus 2. So if I sum them all up, I get something which is proportional to n squared. Okay? So what does that mean? I have n operations, and the time is n squared. That means amortized, it's also order n, okay? It's worst case, the amortized is not better than because all the deletes are expensive, basically. Most of them are. Some fraction of n of them are expensive. So amortized is also n. But what about the clever one, doing check? Okay, so I keep inserting, tuck, 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 tuck. I will run a check once, but only the first time, to make sure that the f is non-nil. But all the further inserts will be pure constant time. And then I do delete. Okay? Okay, I remove, so the f will have one element, I remove it. Then the f will become nil, and I do a check. But the check will put all the elements from R into F. So this delete has order n time, because it's moving all the elements from R into F. But now the F list is pretty big. So if I keep doing deletes, the next delete will be constant time, because F, I just take the first element of F, the next one also, and so on. So it's only the first one that is order n. All the others are constant. Okay, so I have n plus n here. Let's see. No, if I just do this, I have n plus n minus 1, which is 2n minus 1, plus n. So amortized, divided by n, it's a constant. Okay, so the worst case is still n, because there's an n here. But the amortized is constant because this is very rare. It's only once every n operations. You see that? So this one, see how it works, huh? Is it clear how it's working? Okay. Now I can ask a question. This is pure functional programming. So when I run the amortized one, and I create a Q2 out of Q1, the Q1 is still existing. So it's actually also persistent. It's also persistent. So what's going on here? Why do I say amortized one? if I use this one, so the smart one, use it persistently, it will be correct. But what will be the complexity? If I use it persistently, now we have to think a little. If I take this smart one with F and R, and I use it persistently, that means I have multiple versions, then what I can tell you, it's no longer amortized O1. It will be always order n. If I use, so this one is actually not a good persistent algorithm. I mean, it's good if you use it ephemeral, but persistent, if you use it in a persistent way, it's not good. You see why? This is the kind of thinking now you have to, this is important. Because this is the kind of thinking that will be important for the lazy when we have multiple versions. The problem with the difference between ephemeral and persistent is that in an ephemeral, there's only one sequence here. Whereas in a persistent version, we can have branches. We can take this version here and do other inserts, or this version and do other inserts, so we can have branches. But we can take this version right here and do another delete. But that other delete will be order n. Oh. And if I create n versions from this version here, I create n new versions, which I'm allowed to do, persistent. Each of those new versions will take order n to create. And if I create n new versions, each operation will be order n. So it's not amortized O1, it's amortized On. You see that? So if I use this one with multiple versions, I'm not getting the advantage because the new versions do not take advantage of this, what's going on here. If I take a new version from here, it'll always be an On operation. See that? If I do a delete and another delete to create another version and another one, all of them will be n. So I don't have, the On operation is not rare if I have multiple versions. I can have them be very common, depending on how many versions I have. So if I have n versions, it will be On, even amortized. You see that? This is a little bit subtle, huh? So this FR algorithm, which is amortized O1, if you use it in an ephemeral way, it's not efficient as a persistent algorithm, even though it's correct. It's correct, but not efficient. Okay? So let me run the code. It's nice, it's actually nice to see how it runs an algorithm like this, because it's a little bit subtle, and since this is our first kind of non-trivial algorithm, let me show you how it works. Amortized, constant time, ephemeral. So new Q will have both F and R equal nil. Let me define my check, the check function, which basically, if the F is nil, it moves it all to, let me do it like this. It moves all the R's to F using reverse. Let me make this one a little bit wider so I can do it in one line. Okay, so that's my check. Then Q, oh, I forgot a parenthesis here, sorry. And now I can do insert and delete. So basically it's like this, The insert will do F, so it will do this. Let me write it in piece and piece. So the Q is equal to QFR, and it will return F X bar R. Like this. So this is the simple way of doing insert. But this is not good enough because I'm only growing the R, I also have to put elements in the F. So this is why I need to wrap it up in this check function. Huh? So I basically wrap it in check. Okay? And if I do a delete, case x of q fr, then, so the simple operation will take f is equal to x bar f1, okay? So this binds x, and it returns q of f1 r. So this would be the simple one, where it's basically taking an element out of f, and it's becoming f1. But the problem is, what if this f1 becomes nil? Then I have to move the r's to the f again. So again, I have to wrap it in a check. Okay? I have to wrap it in. Whenever I end up, I always have to wrap it in check. What's going on? Check. Oh, it's doing Greek. Just a sec. Why is it doing Greek? Should be doing Greek. Check. Okay? So this is the whole implementation. So it's not that complicated, huh? But it is much more efficient than the previous one. So let me pile this. And let me run it now and see what happens. Okay, so let me create some versions here. Q1 is equal to new Q. Browse Q1. Wait, oh no. I'm sorry. I have to do it to declare here. It's still using the old one. Now it should be better. So this is Q nil nil. Okay? And now I insert Q1, little a. Browse Q2. So what is this going to display? When I look at Q2, what is it going to show me? You tell me. So it's going to run insert now. So it's going to do Q of f x bar r, so f is nil. It's going to do Q of nil, and then a list with a bar nil, and then it'll run check. And check will do up there. So what will be displayed here? It won't be nil followed by a bar nil, huh? See what would be, do you see what would be displayed here? Q, A, and then nil. Do you see why it's like that? So the insert will put that little a at the end, but the check brings it back to the front. Okay? See that? And now let me go farther. Let me do another insert. Q2B. So what will be displayed when I do this? So now you tell me. Somebody has to tell me. What will be displayed now? So I'm using Q2 as the input, huh? So Q2 is that, the second line there, huh? And I'm doing another insert. The code is not so complicated, huh? So what will be displayed here? Oh, I guess it's very early in the morning. Sorry about that.
I can try.
Yes.
Maybe A, B, and then just B.
Sorry, what is the first argument? So what is displayed exactly? Yeah, I'm hearing good things. What is Q3?
So
Say it
QT will be Q, A, B, and then just B?
AB, why AB?
Oh, wait, no.
Go step by step. So
I-
first it will do
I
Q
remove
of
what I said.
Fx bar R. So that is A and B. Two lists.
Yes.
List A and B. And then it runs check. Case Q of Q nil R. But the first argument is not nil, it's A. Which means it doesn't do that, it just returns Q, else Q. So it will be what?
I don't.
Oh, okay. You're forgiven because it's very early in the morning, but it's that.
Oh.
Because the check will only move something into the F if the F is nil. But it's not nil. It's A. So it just makes sure that it's not nil. That's all it does. Okay. Now if I do another one, this time someone has to say it. Huh? If I now insert a third element, what is displayed there? Come on. Now it should be easy, right? Yes, so A, and then BC or CB, because the C is put in front. A, and then CB. Because the check will do nothing now, because the F is not nil. It's not nil. So it's A, CB. So and if we keep doing inserts, elements keep putting there. Now let me do a delete. Okay. Let me create some more Qs. Q5 is delete. And let me put an X here. So it deletes from Q4 and it returns in X. And it will browse Q5, and browse X. Okay? So now I'm taking the list ACB. So that represents the Q ABC. So if I delete an element, then the A is deleted. I return A. Now the F is A, it's in the front of the Q. The A is taken out. But then when I run check, the F1 is nil. So the check will take CB and put it in front. So it will be Q, BC, nil. See that? The check is always guaranteeing it's not nil. That's all it's doing, okay? So it's BC nil. You see how it's working? And the result, so A is the output, it's the front. The F is the front, is A. But when I take A out, I get nil CB. And the check will go, is a nil. And so I have to fill it up again. The check is just making sure the F is not nil. So it will do reverse, it will put BC nil. See how it's working? But that's only done once. And now I have, if BC could be huge long list if I do many inserts. Now I can do lots of deletes, and the check is not going to be run, because the F is not nil, okay? So the delete is only done once for n elements, okay? Okay, so let me go back to this. So basically I did this, I did a bunch of inserts. The first delete is going to run reverse. But the second delete won't run reverse because the F is now a big list, okay? So all these deletes are going to be very fast, okay? So I'm basically collecting all the elements and moving them in one big batch. I move them from R to F. Okay. Okay. Oof. So let me stop here. So we've seen the first kind of clever algorithm. Okay. The first one, which is this one. But this one is still not very clever. This is only scratching the surface. But the next course will be on Friday afternoon, I think, next week, which is great, isn't it? It means we will all be very much awake, right? The next one, the next examples are much more clever than this. This is nothing. You just wait and see the other ones, the new ones coming up. So this is already kind of nice, huh? But this is nothing compared to what we will see when we start using laziness, okay? So you'll see much more cleverness. But that's for next time.